Hello everyone. The title of this video is Solve Quadratic Equations of the form a times the quantity x minus h squared equals k, where a, h, and k are real numbers, using the square root property. Alright, so before I get to the questions, every exercise I'm doing in this video is taken directly from a free online textbook at openstacks.org. It is their Intermediate Algebra 2nd edition text, and I'm in section 9.1 titled Solve Quadratic Equations Using the Square Root Property. And I'm under the heading Solve Quadratic Equations of the form a times the quantity x minus h squared equals k using the square root property. I will only be doing the even numbered exercises, so number 24, 26, 28, all the way down to exercise 46 in this video. You'll notice that the odd numbered problems, you can click on the number and it'll take you to the solution. So I'm doing the ones that don't have a solution posted. I'll also have in the description of this video timestamps for each example. Example 1's timestamp will be for number 24, example 2's for number 26, example 3 for number 28, and so on. Please use those if you wish to navigate the video a little better. And one other request I have is that when I bring up a new question in the video, pause it and try to work it out yourself first before watching me do it and then compare your work to mine. Right, because if you're just watching me do these questions and not practicing yourself, chances are you're not learning all that much. Alright, so the first question is going to be exercise 24. I have these written out as you saw earlier. So again, this is example 1, number 24 from the textbook. And we're asked to solve, right? Just solve and simplify our solutions. We're trying to find, just like any other equation solving, trying to find values that I can replace the variable with to make a true statement. And in every single one of these, we're going to end up using a property that we're calling, the square root property. Which I'll be abbreviating SRP throughout the video. So when you see SRP, that's square root property. Alright, so this states the following. If you have a square, right, a squared, where a is any expression. If a squared equals some number b, then a is either the square root of b, the principal square root, the positive square root of b, or another thing you could square to get b would be the negative square root of b. So, or a could be the negative square root of b. Right, and this, remember, this comes from the fact that every number that's not 0 has two square roots, one positive or one principal square root, and then its opposite. And this will be applied in every single problem we do in this video. Okay? So in example 1, notice that it's already starting out like the form of the equation from the hypothesis of the square root property. We're going to want a square on one side all by itself equal to a number, which is exactly what number 1 looks like. we have a square, right? V plus 10 squared equals a number. All right, and that leads me to another note I want to write for you. You can only use the square root property to solve a quadratic equation. You can only use the SRP when there's a variable inside a square and no variables outside that square. And I pointed this out in the last video on the square root property at the very end. I just didn't write that note down for you. Now I am. So you can only use the square root property when there is a variable inside a square like we have here, right? See, v plus 10, that expression is inside a square, right? It's being raised to the second power. And at the same time, there is no variable outside the square. So you notice the v plus 10, there's a variable v inside the square, and looking outside that square, there is no variable, right? There's no v anywhere else. So this is the only scenario in which you're going to be able to use the square root property. Alright, so see, it starts off the way we want. I have a square on its own side equal to a number, where the a in my square root property here, a is v plus 10, and b is 121. So then I can apply the square root property, right, SRP. By the square root property, this expression being squared, the v plus 10, is either the positive square root of 121, or, again, this expression being squared, v plus 10, is the negative square root of 121. Now the square root of 121, right, is 11. So either v plus 10 equals 11, or v plus 10 equals negative 11. And then we solve these for v, right? Notice that neither one of these has v alone yet. But it would be very simple. I would just simply subtract 10 from both sides. So either v equals 11 minus 10 is 1, or v equals negative 11 minus 10 be negative 21. And then don't forget, you always need to do this. You should always be doing this. Check your answers. Check back in the original equation. Now when v equals 1, you'd have 1 plus 10, which is 11, and 11 squared is 121. Right, so that works. So I'm going to circle that. Right. So v equals 1 is a solution. And then plug in negative 21 for v. Negative 21 plus 10 is negative 11. And negative 11 to the second power would be positive 121. So both of these work. But please don't forget to check your solutions. All right. Now the next question is the same kind of setup. This is number 2. It's exercise 26 from the text. It's set up the way I want to start. You know, like I have here in the hypothesis of the square root property. I have a square, some expression squared on the one side equals, and then a number on the other. So you see this n plus 5 squared on one side equals, and then a number 32 on the other. There's a variable n inside a square, and if you look outside the square, there is no variable. Right? That's prime form for when you can use the square root property. Okay, so by the square root property, this expression n plus 5 is either going to be the positive square root of 32 or n plus 5 is the negative square root of 32. Now you could also write these together as plus or minus. You have n plus 5 equals plus or minus the square root of 32. But for right now, I'm just going to keep separating them. Right. Now the square root of 32, that simplifies to 4 times the square root of 2. Right, the square root of 16 times the square root of 2. But then to get n alone, I would subtract 5. So I'd have n equals, negative 5. I'm subtracting 5. And then here we have plus the square root of 32, or plus 4 times the square root of 2. Or, and then here, subtracting 5, n equals, negative 5 minus the square root of 32, minus 4 times the square root of 2. And again, don't forget to check your results. Now, this time, if you plug in negative 5 plus 4 root 2 for n, the negative 5 and positive 5 would go away, it'd add up to be 0, and you'd be left with just 4 times the square root of 2, or the square root of 32 squared, which would be 32. So this works. This works. And the same thing would happen here if I plug in negative 5 minus 4 root 2. Well, negative 5 minus 4 root 2 plus 5 would get rid of the negative 5, and I'd have negative 4 root 2 squared, or the negative square root of 32 squared would be positive 32 again. So I'd get 32 equals 32. Both of these work. Alright, now here's another way, because some of these won't be so nice, some of these numbers. Another way you can check with a calculator is just this way here. Alright, so I'm going to pull up, I have a TI-84 emulator. You see that here. And what I'm going to do is something that you can really only do on certain calculators, right, where you can take information and store it in a certain variable. So I'm going to enter my one solution here, this negative 5 plus 4 times the square root of 2. Negative 5 plus, and then 4 times the square root of 2. Alright, so that's 0.656, 854, 2495, blah, 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 blah. Or keep going forever. What I'm going to do is store this. Right? I'm going to hit this stow button with the little arrow after it. Store this as a variable. Now, an easy variable to do would be x. If you want to stick with what the problem has, it has n. So you hit alpha, and then look for the green letter N here. That'd be above the log button. So now every time I hit enter, and so now every time I enter the letter N, it is this number. Okay. And now I'll use that to check my equation. Go back to the original equation. Let's put the quantity n plus 5 squared. Right. N plus 5 squared, where n is this 0.656, this negative 5 plus 4 root 2, and square it, and hopefully that'll give me 32. So I'd end up with 32 equals 32. And look at that, it does. Alright, so that's the way I use the calculator to check solutions sometimes. And you can do the same thing for the other number, right? Just enter this number, -5 minus 4√2. So I'll do that one more time. Right? So enter the other solution, -5 minus 4 times the square root of 2. It's -10.656854, blah, blah, blah. I'm going to store this, hit the stow button, store this as n again. Right, so now when I use n, right, enter n there, it's this number. All right, it's this -5 minus 4√2. And now again, I'll check the I'll just enter the one side. We have the quantity, n plus 5 squared. And this time n is the value of -10.656854, and hopefully this gives me 32, the other side of the equation. And look at that, it does. All right, so that's another way, if you wish, if you have a calculator that or you just actually enter this stuff in a calculator and square it and see you get 32. I mean, you can do that with any calculator, but these work, right? And you should always be checking. Great. Alright, so the rest of the questions are very similar to this. I just want to start off by getting the equation to be in this form. Something squared equals a number, where there's a variable in the square and no variable outside the square. And then we can apply the square root property. Alright, so example 3, which is exercise 28 from the text, has some fractions in it, but you should know how to deal with fractions, I'm hoping. But it is in that form already, where the square is on its own side equal to a number. There's a variable in the square, and there's no variable outside the square. So I can apply, I'll go this way, I'll just write SRP. I can apply the square root property. So this x plus 1/5 is either, the positive square root of 7/25, or x plus 1/5 is the negative square root of 7/25. Now the square root of 7/25, usually, again, for this particular text, they don't want fractions inside radicals, right? You would like to have no denominators in a radical. So this is x plus 1/5 equals, the square root of 7 divided by 5, right? The square root of 25. Or x plus 1/5 equals, negative square root of 7 divided by the square root of 25, which is 5, right? Now the denominators are rational. Right? And then I solve for x in each of these, right? And that would just be by subtracting 1/5. So x equals, negative 1/5 plus the square root of 7 divided by 5. Or x equals, negative 1/5, again subtracting 1/5, negative 1/5 minus the square root of 7 divided by 5, right? And both of these, I'll tell you right now, both of these work. If you were to plug them in, you'd get 7/25 equals 7/25. All right, so I'm going to circle both. Now these are great the way they're written. But, like I said before, you could use the plus or minus symbol to kind of shorten your writing. So you could say x equals negative 1/5, plus or minus the square root of 7 divided by 5, right? That's also valid. These mean the same thing. So this just puts both of them together in one line, one with the plus, one with the minus. There are two solutions. Also, I mean, if you notice that these have the same denominator, remember when two numbers have the same denominator, you can put them together with that common denominator, and the numerators would be -1 plus or minus the square root of 7. Alright, so one of the answers is -1 plus the square root of 7, all divided by 5, and the other one's -1 minus the square root of 7, then all divided by 5. Again, all these are equivalent, right? All these are the same. Me personally, though, I do like having my separate solutions written out. Okay. Next question. So it's already, same setup. It's number 30 from the text, example 4. I've got a square on its own side, a number on the other side. The variable is inside the square, and there's no variable outside that square. So I can immediately jump to using the square root property. So this t minus 5/6, that's being squared there, that's going to either be the square root of 11/25, which would be the square root of 11 divided by 5, right? Just simplifying this square root of 11/25 right now, so that the denominator is rationalized. Or the t minus 5/6 is negative square root of 11/25, or negative square root of 11 divided by 5. And then I solve for t in each of these, right? Just add 5/6 to both sides. So one solution is 5/6 plus the square root of 11 divided by 5. Right. The other solution I'm getting, adding 5/6, right? 5/6 minus the square root of 11 divided by 5. And again, I leave it to you to check, but I'm telling you right now, when I plug both of these in for t, the 5/6 would go away because of the minus 5/6, and then you square these 11, square root of 11 over 5 squared would be 11/25. So both of these would work. And again, you can use the calculator like I did with question 2 if you wish. Great. Oh, and these, by the way, these don't have the same denominator, right? So I couldn't put them together like this. I'd have to get a common denominator, but like I said, I usually like to keep them split up, especially when there's square roots involved. Alright, next question. Now, number 5, which is exercise 32 in the text. We have the quantity b minus 1 squared, then minus 9 equals 39. Now this does not look like questions 1 through 4. Right? In questions 1 through 4, the square was by itself. So I'm going to need to do that. Right? We want to do that here. So this quantity squared here, this b minus 1 squared, isolate that. Get it by itself. Isolate the square. Right, so that would just involve adding 9 to both sides. Right, so I'll take this over here. So we have on the left side, the quantity b minus 1 squared, and then 39 plus 9 would be 48. And now I have it in the form that I want, to where I can use the square root property. Right, the square on one side by itself, a number with no variables on the other side. Right, variable in a square, no variables outside that square. Right, so then, by the SRP, right, by the square root property, b minus 1 is either positive square root of 48, which again I'll simplify. The square root of 48 is the square root of 16 times the square root of 3. So that's 4 times the square root of 3. So b minus 1 is either 4 times the square root of 3, or b minus 1 is negative 4 times the square root of 3. And then to solve for b, I would simply add 1 to both sides. Right? So b is equal to, now if I add 1, that's 1 plus 4 square roots of 3, or b equals, and then again adding 1, you get 1, and then minus 4 times the square root of 3. And there you go. And check these, and I leave it to you to check them, but they will both work. Right? So 1 plus 4 times the square root of 3, and 1 minus 4 times the square root of 3. Great. Wonderful. All right, next question. Number 6, which is exercise 34 in the text. Same deal. See, I've got a variable and a square. No variables outside that square, but the square is not alone. Right? So I can use the square root property, but just not yet. Right? So once again, I wish to isolate the square. All right, so the first thing I do would be add 7. So we'd have 5 times x plus 3 squared equals 75. And then I would divide by 5, right? Get rid of the 5. I want this quantity squared, this variable expression squared, I want that alone. So we have x plus 3 squared equals 15. 75 divided by 5, 15. And now I have what I want. Square equals number. So then by the square root property, SRP, x plus 3 is either positive square root of 15 or negative square root of 15, right? X plus 3 equals negative square root of 15. And then I would subtract 3 from both sides. We get x equals negative 3 plus the square root of 15, or x equals negative 3 minus the square root of 15. And that's as simple as those solutions get. And again, I leave it to you to check, but both of these work. Right. Great. All right, next question. All right, so now, number 7, which is exercise 36 from the text. It starts off the way I want. See, I got the variable expression squared on its own side, a number on the other side, right? And there's, the variable d is inside the square. There's no variables outside the square. So this is the way I want it. The only problem is there's a negative number. So we're going to end up with taking the square root of a negative number. So that'll involve imaginary numbers. And don't forget the imaginary unit I. Right? The square root of negative 1, that's going to show up in this problem. So I can apply the square root property right now, right, because it's already a square equal to a number. So by the square root property, this 8d minus 6 is either the principal square root of negative 24, or 8d minus 6 is the opposite of the square root of negative 24, the negative square root of negative 24. And again, you see the square root of a negative number off to the side here. Remember, the square root of negative 24 square root of negative 24, I'm going to rewrite as the square root of positive 24 times I. Make sure that the I is not in the square root. And the square root of positive 24, that's 4 times 6. So that's 2 times the square root of 6 times I. Right. So what I have here is 8d minus 6 equals the square root of negative 24. I'm going to rewrite as 2 times the square root of 6 times I. Or 8d minus 6 equals 2 times the negative 2 times the square root of 6 times I. Alright, then I would add 6 to both sides. And we have 8d equals positive 6 plus 2 times the square root of 6 times I, or 8 times d equals positive 6 minus 2 times the square root of 6 times I. And then I would divide every term by 4. Or sorry, not 4, 8. Both of these have 8 times d. So I divide every term by 8, and I'll simplify right now. So d equals 6 divided by 8 reduces to 3/4 plus, and then 2 times the square root of 6 times I divided by 8. 2 goes in 8 4 times. So I have the square root of 6 divided by 4 times I, right? And if you want, you could put these together because they have a common denominator, make it 3 plus the square root of 6 times I all over 4, but I'm going to leave it like this. Okay? So one solution is a complex number with an imaginary number in it, right? Imaginary part, square root of 6 over 4 times I. Or, and then this one, just dividing everything by 8 again, d equals 6 divided by 8 is 3/4. And then minus, and then 2 times square root of 6 times I over 8. 2 over 8 is 1/4, so we have the square root of 6 divided by 4, and then times I. Here are the solutions. Now this one I'll actually check with the calculator. I mean, you could check with by hand too. Plug these in for d, and you'd have to distribute the 8 and then subtract 6, and you'd be left with basically the square root of 24 times I each time, or negative square root of 24 times I, and then squaring those would give me negative 24. Alright, so you'd end up with negative 24 equals negative 24. Both of these work. But one more time, I just want to show you how to do this on a TI-84 calculator. 83, 84 are very similar. Now, in order to be able to work with imaginary numbers, in order to be able to work with I, you got to make sure that you're in the A plus BI mode and not real mode. And so just hit the mode button, go down and change it from real mode to A plus BI mode. Alright, so I'm going to do the same thing that I did before to check my solutions with the calculator. I'm going to enter this first solution. Alright, 3/4 plus, and then the square root of 6. Get out of there. Then divided by 4. Make sure the 4 is not inside the square root. And then times I, right? And just put the I after that. Remember, it does division first, then multiplication. So this is the square root of 6 divided by 4, and then times I. And I'm going to store this as, d, right? It's alpha d, right? Okay, and it gives some crazy decimal stuff, right? So now every time I use the letter d, it is this number, right? So what I want to do now is go, put in the left side of the equation, the quantity 8d minus 6 squared, and hopefully I get negative 24. And look at that, negative 24 plus 0i, right, which is negative 24. So that solution works, and I leave it to you to check the other one. All right, but they should both work out. Wonderful. All right, so the next question. going to end up being pretty similar. The only difference is I have to get the square by itself first. All right, so number 8, exercise 38 from the text. First, I would have to add 5, right? Get the square alone. So we have the quantity, 2y plus 1 squared equals negative 18. Right? Negative 23 plus 5, negative 18. Now I can apply the square root property, right? You have the variable in a square, no variables outside that square, right? So the square root property will apply. So by the square root property, 2y plus 1 is either positive square root of negative 18, alright, but the square root of negative 18, don't forget, square root of a negative, we're going to write as the square root of 18 times I, right, as an imaginary number. And the square root of 18 is 3 times the square root of 2, alright, so 3 times the square root of 2 times I. So positive 3 times the square root of 2 times I, or this 2y plus 1 equals negative square root of negative 18, or negative 3 times the square root of 2 times I. Alright, then I would add 1 to both sides to get 2y equals 1 plus 3 times the square root of 2 times I, or 2y, oh no, I'm subtracting 1, sorry, so negative 1. Sorry, I would subtract 1 first, so negative 1 plus 3 root 2y. And over here, 2y equals negative 1 minus 3 times the square root of 2 times I. And then I'm dividing everything by 2, to get y alone. So over here, y equals negative 1/2 plus, 3 times the square root of 2 divided by 2 times I, right? That imaginary number. There's one solution, and then again dividing through by 2 here, y equals negative 1/2 minus 3 times the square root of 2 divided by 2 times I. And I leave it to you to check these. These indeed are solutions of this equation. Great. Alright. So now the next questions are a little trickier. Notice, so number 9, which is exercise 40 from the text. Notice that there is a variable outside the square. Variable outside a square. Right, you got n to the second power, there's your square. But there's this other n outside the square. This means that the square root property can't be used, as is. Alright. I can't solve for n squared and then use the square root property. That will not work here. Right. So what are we going to do? I eventually want to use the square root property. Well, hopefully you recognize, and this is a very specialized problem, right? This will not always happen. But hopefully you recognize that n squared plus 8n plus 16 is one of those perfect square trinomials. You may recall what a perfect square trinomial is. If not, I'll refresh your memory over here. So we have, a squared plus 2ab plus b squared, where a and b are just some expression. Any trinomial of this form is a perfect square, can factor as the same factor twice as a plus b squared. Or if you have a squared minus 2ab plus b squared, it'll factor to a minus b, that quantity squared. So again, that might ring a bell. Well, this n squared plus 8n plus 16 is one of these. This is n squared plus 2 times 4 times n plus 4 squared. It's got this form where a is n and b is 4. So that left side factors to n plus 4 to the second power. And you could check it out. Take n plus 4 times n plus 4 and FOIL, and you'll get 8n squared plus 8n plus 16 back. So now the equation looks like this, and this is where I can use the square root property. Right? So now I can use the square root property. Oh, this again, right? SRP. Because there's now just a variable in a square, this n plus 4, and no n outside the square. And the square is all by itself. So by the square root property, this n plus 4 is either positive square root of 27, which is 3 times the square root of 3. Right? Square root of 27 simplifies to the square root of 9 times the square root of 3, which is 3 times the square root of 3. Or n plus 4 is negative square root of 27, or negative 3 times the square root of 3. And then in solving both of those, we'd have n equals, negative 4. Right, I'm subtracting 4 plus or minus 3 times the square root of 3. I'm only doing that because I'm running out of space here. The plus or minus symbol. Remember, this is two solutions. One of them is negative 4 plus 3 times the square root of 3. The other one's negative 4 minus 3 times the square root of 3. And again, the only reason I did this here is because I was running out of room. And I leave it to you to check. Alright, I leave it to you to check. Number 10, very similar. Y squared, there's a square there with a y in it, but there's also y outside that square. So like in number 9, I can't use the square root property on this equation the way it looks right now. Right? If you try, if you solve for y squared and then tried the square root property, it would be really, really messy and bad. But as in question 9 again, y squared plus 12y plus 36 is another one of these perfect square trinomials, where a is y and b is 6. This left side actually factors to y plus 6 to the second power. And then we have equals 32. Right? And look, now I have something where I can apply the square root property. Right? So by the square root property, y plus 6 is either positive square root of 32, which is 4 times the square root of 2, right? Square root of 16 times the square root of 2. Or y plus 6 is negative square root of 32, or negative 4 times the square root of 2. And then I would just subtract 6 from both sides to get y alone. Right? So y equals negative 6 plus the 4 root 2, or y equals negative 6 minus 4 times the square root of 2. And again, if you want to, you can write negative 6 plus or minus 4 root 2. Right? Same thing. Same two solutions. And I leave it to you to check, but they should work if I did everything correctly. Fantastic. All right. So I got one more page here, just two more examples. And they're very much the same as these previous ones, very similar. So number 11, exercise 44. 9y squared plus 12y plus 4 equals 9. Notice there's a variable in a square, y squared, but there's a variable outside that square, so I cannot use the square root property on this equation. But I can rewrite this left side as a perfect square. All right, this is yet again a perfect square trinomial. Again, that doesn't always happen. It's just happening for these specialized examples. 9y squared plus 12y plus 4 actually factors to 3y plus 2 squared. And go ahead and check it. Take 3y plus 2 times 3y plus 2 and FOIL. You will get 9y squared plus 12y plus 4. So I have what I want. Something with a variable in a square equal to a number. All right, and the square is alone. There's no variable outside that square. Now I can apply the square root property. So again, SRP. So 3y plus 2 is either positive square root of 9, which is 3, or 3y plus 2 equals negative 3, right? Negative square root of 9. Solving this equation would give me 1/3, y equals 1/3. Right, subtract 2, then divide by 3. Solving this equation gives me y equals negative 5/3. And again, if I did everything correctly, which I know I did, these are the solutions, and I leave them for you to check. All right. 1/3 and negative 5/3 should make the original statement true. All right. We got just one more question. Number 12, exercise 46 from the text. Same kind of setup as number 11 and number 10 and number 9. There's a variable in a square, x squared, but, right? There's a variable outside that square. So I can't use the square root property on this equation as it looks right now. But, this expression on the left side, 64x squared plus 144x plus 81, is another one of those perfect square trinomials. This is actually 8x plus 9 squared. And you can check that out. Take 8x plus 9 times 8x plus 9 and FOIL. You'll get 64x squared plus 144x plus 81. And now I have the form that I want in order to be able to use the square root property. Variable in a square, no variable outside that square, and the square is all by itself, right? Square on one side, number on the other. So now I'm applying the SRP, right, the square root property. So 8x plus 9 is either the positive square root of 25, which is, positive 5, or 8x plus 9 is the negative square root of 25, which would be negative 5. Right? And I solve each of these. So here's this equation, subtract 9, 5 minus 9 is negative 4, divided by 8 would be negative 1/2. Right, negative 4/8, negative 1/2. Or here, subtract 9, negative 5 minus 9 is negative 14, divided by 8. Right, now negative 14/8 is negative 7/4 when reduced. Right. Fantastic. And I leave it to you again to check these numbers, check that these are solutions to this equation, but they should be if I did everything right. Wonderful, wonderful. So, yeah, so again, I hope after watching me go through these 12 examples here, you understand, when is it appropriate to be able to use the square root property. All right, only when there's a variable in a square and no variable outside that square. All right, and then you get the square alone on one side, a number on the other, then you can apply the square root property. It's very specific. All right, so I'm hoping that watching me go through these 12 questions here helps you, when you're asked to solve quadratic equations in a specific form, using the square root property on your own. And thank you very much for watching.